Now we consider the fifth question in the set of exercises. Omega is an open subset of Rn. And the ball of radius epsilon rho contained in omega. Then U is a twice continuously differentiable. Is harmonic. Harmonic is Laplacian U is 0. Laplacian U, we know that Laplacian U is the sum of the second order partial derivative. Okay, then what we want to prove. The value of U at 0 at origin is n omega n rho below ux dx. This is called the mean value theorem of a harmonic function. Why this is called mean value theorem? So this is the ball of radius rho. Our omega is a larger set containing this ball. So this is omega. So this integral can be considered as the sum of U over the ball. And the factor in front of this integral is the inverse of the volume of the ball, because omega n is the area of the unit sphere. Omega n is the area of the unit sphere. Then using Euler formula, you can prove that the volume of the ball of radius rho is omega n rho n over n. So this is why we call this result the mean value theorem. So how to prove this result? This result is not easy. The case n greater than 2 or less than 2 is different. So we only consider the case n greater than 2. For n less than 2, for n equal to 2, the argument are the same, but you need to make some modification. So for simplicity, we consider the case that the dimension is greater than 2. We consider this function Vx V defined on the ball of radius epsilon. Removing the smaller ball, we take epsilon positive and less than rho. So this is the origin. Okay, we take a rho smaller radius. So this is the ball of radius epsilon. Okay, then we consider the function v defined on the domain bounded by these two spheres. The function v is given by 1 over x n minus 2. So we know that Laplacian v is 0 in this domain. So this function v we already encountered in our previous example. Okay, so we know that the Laplacian v is 0, and the gradient of v we also know. Okay, this this function we already computed before. So we know that Laplacian v is 0, and the partial derivative of v, the directional derivative of v, which is respect to the outward normal vector. So outward normal vector on the sphere of radius rho is point outward, and on the sphere of radius epsilon point inward. Okay. To our domain b rho minus b epsilon. To this domain, the boundary of this domain below removing b epsilon is the two sphere. On the outer sphere, the outward normal vector point outward. On the other hand, on the inner sphere, that is the sphere of radius epsilon, the outward normal vector point to the origin, that is point inwards, which is respect to the ball bounded by which radius epsilon, okay, point inward. But with respect to the domain below removing b epsilon, it points outward. Okay, so we have that the partial the directional derivative is 2 minus n over rho n minus 1. The sphere of radius rho and is n minus 2 epsilon n minus 1 the smaller sphere. This we also computed this before. Let's go back to see. This also is a no result. Here, the last line of this page. The last line of this page. On the sphere of radius epsilon, the directional derivative of v, which respect to the unit normal vector, is dimension m minus 2 over epsilon n minus 1. That is when the radius is epsilon, so the denominator is epsilon n minus 1. So in our case, we have two spheres. The radius are rho and epsilon respectively. Therefore, the denominator is n minus 1, epsilon n minus 1 and rho n minus 1. And the direction of this nu is outward and inward. Therefore, we have a minus sign, difference by a minus sign. So here is 2 minus n, but here is n minus 2. Okay, this is easy. So this is the preparation of our argument. So when we do this, when we do this computation, what we want to apply the second Green identity. We want to apply the second Green identity. So we see that Laplacian u is 0 in omega. Of course, it is also 0. This is also true in this ball. Therefore, we can apply the let's have a look. Okay, we make some parameterization for r in the interval. For r in this interval, epsilon rho, we compute this quantity. The boundary of this sphere, we multiplying the directional derivative of u with respect to the outward normal vector with respect to the ball. This is v is r n minus 2 because vx is 1 over the norm of x n minus 2, but on the sphere of radius r, the norm of x is r. Therefore, v is precisely 1 over r n minus 2. Then multiplying the directional derivative of u, then this is I almost have no place to write, so I need to save space and I change a color. Then this is 1 over r n minus 2 over the ball gradient of u inner product with the outward normal vector. Okay, then applying the divergence theorem, this will give us r n minus 2 integral over the ball divergence of Laplacian of gradient u. But divergence of gradient is just Laplacian. So Laplacian u is 0, so the result is 0. So this is a computation we need in our next computation. Okay, this is a parabolization of our computation. Now we apply the second Green identity by Green second. We have the second Green identity says that omega u Laplacian u v minus v Laplacian u equal the boundary of omega u directional derivative minus v directional derivative surface integral. This is the second Green identity. We apply this second Green identity. We have 0 equal this domain omega, choosing as the ball of radius rho, removing the ball of radius epsilon. Then our u Laplacian v minus v Laplacian u. Why we have this equality? Because both u and v are harmonic. Laplacian u is 0. Laplacian v is also 0 on this domain. Okay, so the integral of this is 0. Therefore, the integral is also 0. Now, by the Green identity, this is the surface integral over the boundary u directional derivative minus v directional derivative of u. Okay, and the boundary of this domain, consists of two parts. So this surface integral can be divided into two integral. The two integral is below u plus the surface integral over the sphere of radius epsilon. Okay, now we consider this term. This term v here is, our v is 1 over, the v here is 1 over rho n minus 2. Because our vx, remember our vx is 1 over x norm n minus 2. On this ball, the norm of x is rho, so the v is a constant 1 over rho to the power n minus 2 over this sphere. Therefore, the v in this term, the v can be moved out of the integral. But then we know that the directional derivative, the integral of the directional derivative of u is 0. We just prove this result in the last step, in the last page. Okay, including the v here. Okay, this computation is 0. We know for every r in this interval. Okay, so using this result, so this term, the integral of this term is 0. Integral of this term is 0. Similarly, the integral of this term is also 0. So these two terms disappear, and we obtain the u plus u epsilon, sorry. Okay, so but the directional derivative of v, which is respect to the unit normal vector, had been computed before. In this part, I will circle it out. That is here. Okay, we already computed these two directional derivative of v, which is respect to the unit outward normal vector nu on the boundary of on these two parts of the boundary of our domain. That is the sphere of radius rho and the radius epsilon. Okay, so using this result, our substituting that result into this will give us that is 2 minus n rho n minus 1 plus n minus 2 epsilon n minus 1 u. Okay, so that is because the left hand side is 0, so we see that the sum of these two are 0, and this tells us that this gives us the following conclusion. 1 over rho n minus 1 equal epsilon n minus 1. Okay, you cancel the 2 minus n and move this part to the right, to the left, give us the identity I just write here. And because the rho n minus 2 is a constant, can move out of the integral. Okay, this can move out of the integral. So you, after move this out of the integral, you cancel the factor n minus 2. You will obtain this equality. And this equality by the so this is the sphere of radial epsilon. So this surface integral, using the mean value property again, we have a point. We can find a point x epsilon on the sphere, such that this integral equal epsilon n minus 1 u at x epsilon, multiplying the area of this sphere of radial epsilon. But this area is precisely omega n epsilon n minus 1. So the result is the epsilon n minus 1 cancel with the denominator in front of this will give us omega n u x epsilon. Then when epsilon goes to 0, this will converge to omega n u 0. So we obtained the left hand side does not depend on epsilon. So we let epsilon go to 0. We obtained u0 is omega n log n minus 1. Okay, so we prove this equality. This is also called the mean value property because the area of the sphere is precisely omega n rho n minus 1. So this means that for a harmonic function u, the value of u at the center of the sphere equal the mean value of the function over the sphere. Okay. Now, but this is still not the result we want to prove. We want to prove the mean value over the ball, not the sphere. What to do this? Okay, we apply the Euler formula. Using Euler. Again, we see that this can be written by 0 to rho dr. The surface integral over the sphere of radius r u d sigma. But this is by the result we just proved. This is 0 rho u0 omega n r n minus 1 dr. Then this is omega n u0 the integral of 0 rho r n minus 1. So this is omega n rho n over n u0. So divided this on both sides, you obtain the equality we want to prove.